Welcome to Module 3, Protocols and Models. This is a theory-heavy module, no CLI today. Frame it as the why behind everything they configured in Module 2. Understanding protocols and layered models is what lets them troubleshoot intelligently later, instead of just memorizing commands. Objective: explain how network protocols enable devices to access local and remote resources. Preview the topic table on screen: rules, protocols, protocol suites, standards organizations, reference models, encapsulation, and data access. This module builds toward the OSI and TCP/IP models, so set that expectation now. Run this as an actual discussion, not a rhetorical question. The broken car in a foreign country scenario is meant to surface the rules any communication needs on its own: language, timing, acknowledgement, before you introduce the formal networking vocabulary. Let a few students propose their own, quote, communication models first. All communication, human or network, needs three elements: a message source, sender, a message destination, receiver, and a channel, the media the message travels over. Just having a wire or wireless link isn't enough. Devices still need to know how to communicate, which is where protocols come in. Protocols are the rules governing how a message is sent, whether face-to-face or over a network. The letter-writing analogy is the one to lean on for the rest of this module: an address, a format, and a delivery process. Every networking analogy coming up ties back to this one, so make sure it lands. Before any communication happens, four things must be established: an identified sender and receiver, a shared language, agreed-upon timing, and confirmation requirements. Compared to a poorly formatted letter, if the address or language is wrong, it doesn't matter how good the message content is. This slide is just a preview list: 5 things every network protocol handles: message encoding, formatting/encapsulation, size, timing, and delivery options. Each gets its own slide next. Tell students this is the backbone of the rest of Section 3.1, so they know what's coming. Encoding converts information into a transmittable form. Decoding reverses it. Humans do this naturally, converting thoughts into speech. Networks encode data into electrical, light, or radio signals, depending on the medium. Keep this brief. It's mostly set up for message formatting next. Encapsulation is placing one message format inside another, like a letter inside an envelope. If the address or the envelope format is wrong, the letter won't be delivered. Same idea for network messages needing correct headers. De-encapsulation is just this process in reverse, at the receiving end. Just like people break long thoughts into sentences, networks break messages into smaller pieces sized to what the protocol allows, rather than sending one giant continuous stream. This directly sets up 3.6 data encapsulation later in the module, where segmentation gets its own deep dive. 3 parts to message timing: flow control, how much and how fast data moves; response timeout, how long to wait before giving up; and access method, who gets to transmit and what happens on a collision. Both devices back off and retry. Real-world analogy: talking over each other on a call. 3 delivery methods shown on screen. Unicast is 1-to-1, multicast is 1 to a selected group, and broadcast is 1 to all. Have students think of real examples. Unicast is a phone call, multicast is a group text, broadcast is a PA announcement. This vocabulary reappears constantly later in the course. 4 protocol types: network communications, IP, TCP, HTTP, the actual data-moving protocols; network security, SSH, SSL, TLS; routing protocols, OSPF, BGP, how routers pick paths; and service discovery, DHCP, DNS, finding devices and services automatically. Don't expect memorization yet, just recognition. Every device along a message's path, sender, intermediary, and receiver, must speak the same protocol, or the message doesn't make it through. This is why protocol mismatches break connectivity, even when the physical wiring is perfectly fine. Reinforces why protocol isn't just jargon. It's the actual agreement making communication possible. Walk through what happens when a device requests a web page, shown on screen. Multiple protocols stacked together, each with its own job. HTTP governs the content and client/server interaction, TCP handles reliable delivery, IP handles addressing and routing, Ethernet handles the physical LAN delivery. This diagram is the bridge into protocol suites. Next. A protocol suite is a group of interrelated protocols working together, best visualized as a stack, where each layer depends on the one below it. The face-to-face analogy works well here. A physical layer, voice; a rules layer, common language, turn-taking; and a content layer, what's actually said. 4 historical protocol suites, shown on screen. TCP/IP, the open standard that won out, maintained by IETF. OSI protocols, ISO/ITU, largely replaced, but its 7-layer model still matters. AppleTalk, proprietary, retired 1995, and Novel NetWare, proprietary IPX, also retired 1995 in favor of TCP/IP. Concrete walkthrough. HTTP, TCP, and IP each operate at their own layer between a web browser and a web server, with Ethernet, or WLAN/cellular, handling the actual physical delivery underneath. TCP/IP has no protocols of its own at the network access layer. That job belongs to LAN/WLAN standards. This table is worth memorizing. It maps the 4 TCP/IP layers to their real protocols. Application, DNS, DHCP, HTTP, SMTP, POP. Transport, TCP connection-oriented, UDP connectionless. Internet, IP, ICMP, OSPF, EIGRP, ARP, and network access, Ethernet and similar. This exact table will resurface throughout the course. Full walkthrough of a web server sending data to a client shown on screen. User data gets wrapped in a TCP segment, adds a header, then an IP packet adds another header, then an Ethernet frame adds header and trailer, each layer nesting the previous one like an envelope inside an envelope. Open standards are why an Apple laptop can pull a web page from a Linux server. Both speak the same TCP/IP protocols. Tie in the tire analogy. Different manufacturers, same fitment standard. Standards organizations are typically vendor-neutral, non-profit bodies specifically to prevent any one company monopolizing the market. 4 Internet standards bodies, shown on screen. ISOC promotes Internet development broadly. IAB, overall management of Internet standards. IETF writes the actual RFCs, the technical specs. And IRTF, long-term research like anti-spam and crypto. IETF is the one they'll hear referenced most in the field. 4 electronics/communications standards bodies, shown on screen. IEEE, 802.3 Ethernet, 802.11 WLAN, the ones most relevant to this course. EIA, wiring and equipment rack standards. TIA, radio, cellular, VoIP, and ITUT, video compression, DSL, one of the oldest bodies. IEEE 802.3 and 802.11 are worth calling out by name. 4 benefits of a layered model, shown on screen. Assists protocol design, fosters competition, vendors can interoperate, isolates change, a fix in one layer doesn't ripple into others, and gives everyone common language. You can't watch packets travel the way you'd watch a car on an assembly line. Layering is how we make an invisible process manageable. The OSI 7-layer stack, shown on screen top to bottom. Application, presentation, session, transport, network, data link, physical. OSI describes what each layer must do, not how. Students will hear these layers referred to by number far more often than by name. Layer 3 feet means network. Layer 2 feet means data link. Drill that numbering now. The TCP/IP model shown on screen has only 4 layers: application, transport, internet, network access. Unlike OSI, TCP/IP is both a protocol model and a reference model, since it closely matches its own actual protocol suite. Point out this is the model that matters most practically, even though OSI's vocabulary still dominates conversation. Side-by-side comparison on screen. OSI's application, presentation, and session layers all collapse into TCP/IP's single application layer. OSI transport maps to TCP/IP transport. OSI network maps to TCP/IP internet. OSI data link and physical map to TCP/IP network access. This mapping is a common quiz question. Make sure it's clear before moving on. Segmentation breaks a large message into smaller units instead of sending one massive stream, like sending a long letter as postcards instead of one huge parcel. 2 benefits: multiplexing, multiple conversations interleave on one link, increasing speed, and efficiency. Only a failed piece needs resending, not the whole message. Segmentation creates a new problem. Pieces can arrive out of order. TCP solves this with sequence numbers, same as numbering pages of a 100-page letter sent in separate envelopes so the receiver can reassemble them correctly. TCP is specifically responsible for this sequencing job. Each layer adds its own header as data moves down the stack. This is encapsulation, and the data's new form at each layer gets a new name, APDU. Shown on screen, data, application, becomes a segment, transport, then a packet, internet/network, then a frame, network access gets both header and trailer. Concrete walkthrough of encapsulation moving from web server to client. User data becomes a TCP segment, header added, becomes an IP packet, another header added, becomes an Ethernet frame, header and trailer added. Emphasize this all happens on the sending side before the frame ever touches the wire. De-encapsulation is the same process in reverse at the receiving host. Headers get stripped off one at a time moving up the stack, from raw bits to Ethernet frame, to IP packet, to TCP segment, to user data, until the original application layer content is recovered and displayed to the user. Network layer and data link layer addresses both help deliver data but serve very different jobs. Network layer IP addresses handle end-to-end delivery across the whole path, while data link layer MAC addresses only handle one hop at a time. This distinction is the whole point of the rest of Section 3.7. An IP address is the Layer 3 logical address that gets a packet from its true original source to its true final destination. Walk the example on screen. BigC1's source IP and the web server's destination IP stay exactly the same throughout the trip, regardless of how many networks or routers the packet crosses. When PC1 and an FTP server share the same IP network, confirmed because the network portion of both IPv4 addresses matches, the Ethernet frame goes directly from one device to the other in a single hop, no router needed. This is the simple case. The next few slides build toward the more complex remote network case. On Ethernet, data link addresses are called MAC addresses. When sender and receiver share a network, the frame is addressed directly device to device. Source MAC is PC1. Destination MAC is the FTP server. Contrast the MAC addressing, device to device, against the IP addressing, network to network, shown in the same diagram. Now the scenario changes. What happens when PC1 talks to a device on a remote network, crossing at least one router? The next few slides split this into two separate questions. What happens to the network layer address? And separately, what happens to the data link layer address? Set that framing clearly before moving on. Key insight, shown on screen. Source and destination IP addresses stay exactly the same across every hop, even through multiple routers. PC1's IP and the web server's IP never change end-to-end. Only the network portion differing between source and destination is what tells the devices they're on different networks. Contrast with the last slide. Since the destination is remote, the Ethernet frame can't go straight there. It goes to the default gateway, router first, since that's the only device PC1 can reach directly. Destination MAC is the gateway's MAC, not the web server's. The MAC address then changes at every subsequent hop, while the IP addresses do not. Summary of the Layer 2 versus Layer 3 distinction. Data link. MAC addresses only deliver a frame one hop at a time and change at every hop. Network layer, IP addresses, handle end-to-end delivery and stay constant the whole way. Before any packet hits the wire, it must be encapsulated into a data link frame first. Close the module walking each bullet as a recap. Source/destination/channel and protocols governing them. The 5 protocol requirements. Protocol suites with TCP/IP as today's standard. Standards organizations keeping things open. OSI's 7 layers versus TCP/IP's 4. Encapsulation/de-encapsulation. And IP addresses staying constant while MAC addresses change hop by hop.